Let's do a quick recap of stat mech terminology. Just because it's a little bit foreign to what we're used to. So we used this epsilon here. This is the energy of a single particle state. In this case, these parameters are going to be like, if it's particle in a box, it's going to be those quantum numbers, it's going to be the volume of the box, it's going to be the temperature. Actually, no, not the temperature, for that one. We had the concept of an energy state. Right, so an energy state is a unique set of conditions. And that's going to be based on the model that we're adopting. So in the case of a non-interacting particle, the energy state is going to correspond to individual properties with respect to, let's say, the velocity in the x direction, the velocity in the y direction, the velocity in the z direction. So for a quantized system, we break that down into those parameters that we talked about, Lx, Ly, and Lz. If there's rotations, it's exactly saying what rotational state are you in, or what vibrational state are you in. It's an exact set of states because we need to calculate and sum up all the states in order for us to get a time averaged estimate of the properties of the system, right? That's the ergodic principle. So the reason why we're adding up all the energy states that are unique is that we can sort of have a complete ensemble measurement and estimation of what's going on in the system. We also have energy levels. Right, so we can have the energy of a particular energy state, that's going to be its energy level. We're going to have degeneracy as a function of the energy. So omega lowercase is what we use for the degeneracy of a single particle, meaning that's the number of different energy states that have the same energy level for a particular energy, is the degeneracy. And then we also have omega. In this case here, this would be omega for a collection of particles. This degeneracy of many particles. Now this omega term right here, this is actually also called the Microcanonical Ensemble. We'll talk about that probably next week early on. The Microcanonical Ensemble is the NVE ensemble, as opposed to what we talked about on Wednesday, which was the Canonical Ensemble, which is the NVT or NV beta ensemble. Now the reason why we adopt sort of the same nomenclature here is that the degeneracy, meaning the number of different states that the canonical ensemble has, is the degeneracy of that energy level. So that's why we use those terms right there. Now the NVE system, equilibrium is established at maximum entropy. And that's where we get the Boltzmann equation that corresponds to the entropy relating to the number of states in the system. Right, so the degeneracy is the number of configurations that all have the same energy. And that's where we get our sort of microscopic interpretation of entropy, meaning that it's randomness of the number of configurations in the system. Now, Q we use for the canonical partition function. Canonical partition function. And the canonical partition function is equal to the summation over all of the states of the system, where the energy is scaled by this parameter beta, where beta, now we haven't shown this, but as we march along, and I don't think we'll have time today because of the quiz, right, we'll show that this beta here corresponds to 1 over kBt, and this is established through, at least in the Sandler book approach, by relating between the conclusions of stat mech to the conclusions of classical thermodynamics. But from a statistical mechanics perspective, this beta is just a property of the infinite reservoir that connects the two. But in a classical analogy, that's the temperature of the reservoir. Then we have that the probability of the system being in state I with some energy level E alpha is going to be equal to a Boltzmann factor divided by the partition function, right? The partition function is all of the states, and this is the normalization constant that has to be true such that the probabilities always add up to 1. Now from here, it was sort of recognized that the internal energy of the system is the average energy, which is a weighted summation of the probabilities multiplied by their energy. So it's an averaged summation, weighted average. And based on the form, mathematical form of all of this, it works out such that the partial derivative of the partition function with respect to beta gives us the internal energy of the system at constant number of particles and a constant volume. So in this case, only changing the temperature. So in some ways, you could think of this as the internal energy is how the density of states changes with respect to temperature. Okay. It's a foreign terminology. Do we feel okay about it for now? Any questions about the terminology for statistical mechanics?
And that one's on our equation sheet, right?
Yes, it is, yes. I think I have most all of the canonical partition function equations on the sheet, which is mostly, we'll be working in probably either the canonical or the microcanonical for basically all the questions that we're working with on exams, and just exams, I guess, from this point onwards in StatMech. What do I have on there? Okay, let's do that equation sheet for a second. Let's see, I've got the partition function, indistinguishability, beta, Helmholtz, internal energy, pressure, and entropy. Yeah, so it's all canonical. Yes.
So partial log Q, that would be the Helmholtz energy, right?
So on the equation sheet, you want to read it out to me. So the Helmholtz energy related for the canonical partition function is
It's top right in that little thing.
Minus KBT log Q. Yeah, so that's,
yeah. So in the case of the classical analogy and representation, right, in the canonical ensemble, the NBT, this is exactly equivalent to the native variables of the Helmholtz energy. So it makes sense that the canonical partition function is directly related to the free energy of the system through the Helmholtz. Now in the case of the microcanonical, so in this case here it's NBT, the entropy is equal to minus KB ln of omega in the NVE ensemble. And this is again exactly the same relationship that we have for classical thermodynamics, where maximum entropy is established I might get this wrong. I don't remember if there's a negative here.
there is.
In the Boltzmann equation.
Mm-hmm.
Okay. I'll pull this one off the top of my head. I can't remember if there's a negative.
There is, yeah.
So then you can also have different partition functions for like NPT, right, which is I think the Sandler book calls it the
Canonical.
Well, the grand canonical is a constant partial chemical potential, but the NPT, the book Sandler uses, I believe, I don't remember what Greek letter this is here, but I believe the book calls it just like a isothermal isobar partition function, nothing particularly novel sounding. But in terms of understanding the principles of StatMech, these two are the way to go. And that's what I'm trying to get across mostly here, is understanding the principles. Any other questions? So remember, the idea here is that the canonical partition function, and again, we haven't actually derived this, we'll talk about this as we go through it, but I just want to draw that connection. How we derived the canonical partition function was basically by applying the principle of the equal a priori hypothesis, meaning that if different energy states have the same energy, they have the same probability. and that this sort of functionality just comes out of that as a consequence. Now, the whole reason why we're doing all of this is due to the ergodic hypothesis. The ergodic hypothesis says that if I can count up all of the states of the system and manipulate it, that is going to be equivalent to taking a time-averaged measurement of the properties of the system, right? The thermometer in a glass of water is measuring a time-averaged property of the temperature, so we can get to that same conclusion by a statistical average. So if we can count all the states, then we should get an accurate representation. But again, these are sort of the principles that are built upon it. And we kind of have to believe them to be true, and as it turns out, they work out really well. But you can run into a situation where people will do simulations that are in the published literature where ergodicity isn't confirmed. And it's a big red flag when you read a paper that you're not necessarily sure that it's going to be ergodic. Okay, so before we can get to effectively the ideal gas law, that's our objective. We want to get to the ideal gas law from the canonical partition function. But before we can do that, there's two hurdles we have to get over. Number one is we have a problem where we can have multiple energy modes. For example, we can have translation in X, translation in Y, translation in Z. We can also have rotation, we can also have vibrations, we can have electronic transitions. So molecules are more complicated than just a ping pong ball, right? So how do we handle multiple energy modes? And two, how do we handle multiple particles? In this case, we'd have to distinguish between whether or not they're distinguishable particles, atoms of two different types that have two different properties, or indistinguishable particles, which are identical based on the Heisenberg uncertainty principle. So let's say we have a molecule, a diatomic molecule like oxygen, for example. Okay, and we're going to limit it to 3 translational modes and 3 vibrational modes. Now this is the early stages of building up a stat mech theory. Right, what we're going to be doing is we're saying, okay, let's just say, for example, that this particle can only have a velocity in x of 1, a velocity in y of 1, and a velocity in z of 1. Right? Those are the only options it has. For the energy, for the vibrational modes, or let's do rotation, sorry. Doesn't matter. Rotation is the next lower energy level. Vibrations are actually higher energy. And let's just say, for example, it has 3 different rotational modes of different speeds or different orientations, whatever the case is. I think for oxygen, it should only actually have 1 vibrational mode, or rotational mode. But let's just say hypothetically that it has 3. What we can write then is that the energy of the particle, let's see, so we can have if the translational modes and the rotational modes are independent, how many different total states do we have in the system? At this stage, it's an easy one. I heard someone say it already. It's 9. Right? So we can have every single one of the translational modes can be any one of the 3 here, any one of these ones can be there. So we have 9 total. So if we were to write that out, right, we would have energy translation 1, energy rotation 1, energy translation 1, energy rotation 2, energy translation 1, energy rotation 3, and then we just keep on listing these out. Translation 2, energy rotation 1, and so on and so forth until we list all 9 of them out. So what we want to write now is the single particle partition function for this simplified system. Our objective here is we're writing a simplified system, and then from the simplified system, we are going to be generalizing it and scaling it up. So the single particle partition function is the summation of all of the different states scaled by this parameter beta. So we'll write this out as e to the minus beta epsilon translation 1 plus energy rotation 1 plus e to the minus beta epsilon translation 1 this one here because I think we'll get the idea. Okay, you can write that out all 9 times. That's our single particle partition function. Now, from exponent properties, if I add 2 numbers together in an exponent, how can I rewrite that?
Just E, the product of 2. Yeah.
They're multiplied together. So in this case here, it'll be E minus beta epsilon T1 multiplied by E to the minus beta epsilon rotation 1 plus a bunch of other junk, right? We repeat this process a bunch times over again. So then what we can do is we can start to factor this. So what I will do is I'll factor out, right, for example, for a collection of this row here, I'll factor out this term here. So it'll be the same. So it is E to the minus beta epsilon translation 1 multiplied by R1 plus R2 plus epsilon R3. And then we do the same thing for everyone following along. I don't want to write out a million different things, so hopefully the pattern is emerging. And then this is going to be exactly equivalent to multiplied by the same thing but for rotations. So we're just factoring this out. So then what we'll do ultimately is we will write the single particle partition function as the product of 2 independent partition functions, which is the partition function of translation multiplied by the partition function of rotation.
And that works with every other mode too, like
It only works with independent energy modes. So in the case of an ideal gas that's dilute, we can assume this is going to be the case. Now, modern stat mech approaches will not be following this approach because for gases, it's really easy, right? We don't even really need stat mech too much for gases. Continuum equation states are quite good. Now, in the case of, let's say, a dense fluid like a liquid, this is going to be a challenge because the rotational energy modes of, let's say, something like normal heptane is not going to be independent of the density of the fluid. So the multiple energy modes being independent is not going to be appropriate. Now, in this circumstance here, if the energy modes are completely independent, if the vibration is independent from the rotation, is independent from the translation, is independent from the electron transitions, right? Then we can write them all out this way. Now in this case here for translation, we didn't have a chance to show it, but we can then further break this down into the translation in the x, the translation in the y, and the translation in the z. And what this really just allows us to do is to simplify the mathematics of the problem. Now the other thing that's nice about all of this formatting here is that when we actually go to calculate the internal energy of the system, it's the natural log of the partition function. Now we didn't talk about indistinguishability, but if we have indistinguishable particles, the partition function for a collection of particles is going to be the individual particles partition function normalized by what we call an indistinguishability factor. And please don't make me write that out. So if you have particle 1 that's in energy state 1 multiplied by particle 2 that's in energy state 2 multiplied by particle 3 that's in energy state 3, right? That's why we have q to the n power, right? So same thing like flipping a bunch of coins. So a coin has 2 sort of states, heads or tails, right? So you have a 1 in 2 chance times a 1 in 2 chance times a 1 in 2 chance times a 1 in 2 chance. So the fact that the probability that the system is going to be in a collection of states is going to be those partition functions multiplied together. Now this term right here corresponds to the fact that it doesn't matter what we call particle 1, what we call particle 2, what we call particle 3, right? It reduces the total number of states because you could swap any two particles at the same time. Now the way that we kind of justify this is if you have 3 bins and 3 particles, if these particles are indistinguishable, how many different ways can I put these particles into these boxes necessarily? So this one here we have 3 choices, 2 choices, 1 choice. If they're distinguishable, that means that there's 3 times 2 times 1, 6. Since they're indistinguishable, that means we need to divide by that number. So that's the indistinguishability factor. So it's probability that when you swap 2 particles, that it's actually the same exact configuration. So now the objective is, well, we'll talk about it on Monday, is we have now a methodology to organize all of the different individual rules for a single particle, right? So these are the rules that a single gas particle has to behave by. Here is how it behaves as a collection of particles. So all we need now is a model that we know what is the energy of a particular energy state for translation, what is the energy for a particular energy state with respect to rotation, what is the energy with respect to an energy state of vibrations. And that's how you get this sort of laws where you're like, oh, well, monatomic gases have an energy of 3/2 kBt. Diatomic have 5/2 kBt. That's because for diatomics, you have a rotational mode plus 3 translational modes. Right? So the thing is, for rotations, we choose a rigid rotor model. For translations, we use particle in a box. For vibrations, we use a harmonic oscillator. Now these are models that we use, and then we just follow through the mathematics of statistical mechanics. We develop the partition function, we differentiate the partition function, and we get the internal energy. So now when we talk about molecules and atoms and we argue about them at conferences, we don't have to argue about what is the property of a bulk heptane fluid versus a bulk water fluid. We can now argue about how does their translation different from the rotation, different from their interactions and things like that. So it simplifies the problem to more fundamental physical interactions. All right, exam 2 weeks from today. I'll post a practice exam next week so we can get ready for that. And it's going to be stat mech from here on out. On the homework, it's going to be still carrying over a lot of classical. For exam 2, it's going to be probably 80 to 90% classical thermodynamics, maybe only a little bit of stat mech. So brush up on those. See ya.